Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In 1905, a 26-year-old patent clerk in Switzerland forever changed humanity's understanding of reality itself. Albert Einstein's special theory of relativity didn't just challenge scientific convention, it shattered our most basic assumptions about time and space. What if everything we thought we knew about the universe's fundamental structure was incomplete? What if time itself could be stretched, compressed, and manipulated? Before Einstein, time was absolute. Sir Isaac Newton's clockwork universe ticked forward uniformly, second by second, everywhere and always. Time flowed like a river, carrying all events at the same relentless pace regardless of location or circumstance. This seemed self-evident, matching our everyday experience where clocks synchronize and moments pass identically for everyone. Einstein's revelation emerged from a deceptively simple question: what happens when we approach the speed of light? His answer introduced space-time, a four-dimensional fabric where space and time interweave inseparably. In this new reality, time becomes malleable, responsive to motion and gravity in ways that boggle the mind. The implications struck at the heart of existence itself. Time dilation means that identical twins could age at different rates. A traveler accelerating to 99% the speed of light would experience time crawling to a near standstill compared to Earth. Minutes for the traveler could equal years for those left behind. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. This isn't science fiction, it's measurable reality. Global positioning system satellites orbiting Earth must account for time dilation effects. Without relativistic corrections, GPS navigation would drift by miles within hours. The satellite's atomic clocks, racing through space at thousands of miles per hour, tick slightly slower than identical clocks on Earth's surface. Particle accelerators provide even more dramatic evidence. Moons, subatomic particles created when cosmic rays strike our atmosphere, have lifespans measured in microseconds. At relativistic speeds, however, these particles exist far longer than their natural decay time should allow. Time dilation extends their existence, letting them reach Earth's surface when they should have vanished high in the atmosphere. The conceptual leap required acceptance that time isn't universal. There's no cosmic clock keeping universal time. Instead, every observer carries their own time frame, their own slice of space-time. What seems simultaneous to one observer might occur at different moments for another moving at high speed. Einstein's equations revealed something even more extraordinary. Gravity itself warps space-time. Massive objects create curves and dips in the fabric of reality, like bowling balls placed on a stretched rubber sheet. This curvature is what we experience as gravitational attraction. Near massive objects, time runs slower. How a clock placed near a black hole would tick more slowly than an identical clock in deep space. This gravitational time dilation means that the phrase "time flies" takes on literal meaning. Time genuinely moves faster the farther you travel from massive objects. The mathematics supporting these concepts emerge from Einstein's field equations, 10 interconnected differential equations describing how matter and energy curve spacetime. These equations predict phenomena that seem impossible: time travel to the future through acceleration, the existence of black holes where time stops, and the expansion of the universe itself. Modern physics has confirmed Einstein's predictions with extraordinary precision. Atomic clocks flown on airplanes return slightly ahead of identical clocks left on the ground. The Hayfel-Keating experiment in 1971 measured time differences of mere nanoseconds, exactly matching relativistic predictions. As we stand on the threshold of understanding time manipulation, we must ask, what would it mean for humanity if we could truly warp time itself? The mathematics underlying Einstein's relativity theories reveals the precise mechanisms governing time's flexibility. At the heart of special relativity lies the Lorentz factor, a deceptively simple equation that quantifies how time stretches as objects approach light speed. This factor, represented by the Greek letter gamma, equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. When velocity remains small compared to light speed, roughly 186,000 miles per second, the Lorentz factor barely differs from 1. Time dilation remains negligible. However, as velocities increase toward relativistic speeds, the mathematics becomes dramatic. At 90% light speed, the Lorentz factor reaches approximately 2.3, meaning time passes more than twice as slowly for the moving observer. The curve steepens dramatically as we approach light speed. At 99% light speed, the factor jumps to 7. At 99.9%, it reaches 22. The mathematics reveals why light speed represents an absolute barrier. The Lorentz factor approaches infinity as velocity, approaches light speed, requiring infinite energy to accelerate massive objects to that threshold. Einstein's field equations extend these concepts into the realm of gravity and curved spacetime. These 10 interconnected differential equations describe how the presence of matter and energy warps the geometric structure of spacetime itself. The left side of each equation describes spacetime curvature, while the right side represents the stress-energy tensor, essentially the distribution of matter and energy. The simplified form, often written as G equals 8 pi t divided by c, to the fourth power encapsulates one of physics' most profound insights: geometry equals physics. The G represents Einstein's curvature tensor, describing spacetime's shape. The T represents the stress-energy tensor, describing matter and energy distribution. The proportionality constant involves pi and the speed of light, connecting geometry to physics through fundamental constants. Gravitational time dilation emerges from these equations through the metric tensor, a mathematical object describing space-time intervals near massive objects. The Schwarzschild metric, derived from Einstein's field equations, describes space-time around spherically symmetric massive objects. This solution predicts that time runs slower in stronger gravitational fields. The mathematical relationship shows that time dilation factor equals the square root of 1 minus 2 times the gravitational parameter divided by the distance times the speed of light squared. Near Earth's surface, this factor differs from 1 by only about 7 parts in 10 billion. However, near extremely massive objects like neutron stars or black holes, the effect becomes enormous. Practical applications require extraordinary precision. GPS satellites orbit at altitudes of approximately 12,500 miles, experiencing both special relativistic effects due to their orbital velocity of about 8,700 miles per hour, and general relativistic effects due to Earth's weaker gravitational field at that altitude. The special relativistic effect causes satellite clocks to run slow by about 7 microseconds per day. The general relativistic effect causes them to run fast by about 45 microseconds per day. The net effect means satellite clocks gain approximately 38 microseconds daily compared to Earth-based clocks. Without corrections for these relativistic effects, GPS positions would drift by about 6 miles per day. The system compensates by adjusting satellite clock frequencies before launch, effectively pre-correcting for the known relativistic effects. The mathematics also predicts more exotic possibilities. Solutions to Einstein's field equations include rotating black holes described by the Kerr metric, which theoretically permit closed time-like curves, mathematical pathways through spacetime that loop back to earlier times. While these solutions exist mathematically, their physical realizability remains hotly debated. Wormhole solutions, first discovered by Carl Schwarzschild and later developed by Einstein and Nathan Rosen, represent another mathematical curiosity emerging from the field equations. These Einstein-Rosen bridges could theoretically connect distant regions of spacetime, potentially enabling faster-than-light travel through geometric shortcuts rather than velocity. The mathematics underlying time manipulation extends beyond pure theory into experimental verification, setting the stage for understanding how these principles might enable practical time-warping technologies. Throughout the cosmos, nature provides a vast laboratory demonstrating time dilation effects on scales both subtle and extreme. From the mundane precision required for satellite navigation to the mind-bending temporal distortions near cosmic monsters. The universe showcases Einstein's predictions in remarkable detail. The most familiar example orbits overhead every day. GPS satellites experience measurable time dilation effects that accumulate rapidly without correction. These spacecraft circle Earth at velocities of approximately 8,700 miles per hour, while experiencing weaker gravity than objects on the surface. The interplay between special and general relativistic effects creates a net time advancement of about 38 microseconds per day. This seemingly tiny difference would render GPS navigation useless within hours. Position calculations depend on precisely timed signals traveling from satellites to receivers. If satellite clocks drifted by even microseconds, calculated positions would shift by miles. The system compensates by adjusting satellite atomic clocks to run slightly slow before launch, pre-correcting for the known relativistic effects. Moving beyond Earth's immediate vicinity, we encounter more dramatic examples. The Parker Solar Probe, launched in 2018, represents humanity's fastest spacecraft, reaching speeds exceeding 430,000 miles per hour during its closest solar approaches. At these velocities, special relativistic time dilation becomes measurable, though still tiny. The probe experiences time approximately 1 part in 10 billion slower than Earth-based observers. Cosmic rays provide natural particle accelerators, demonstrating extreme time dilation. When high-energy protons from deep space collide with Earth's upper atmosphere, they create showers of secondary particles, including muons. These unstable particles normally decay within about 2 microseconds, far too quickly to reach Earth's surface from their creation altitude of roughly 9 miles up. However, cosmic ray muons travel at velocities exceeding 99% light speed. Time dilation extends their lifespans by factors of 10 or more, allowing them to survive the journey to Earth's surface. Detectors regularly record these particles, providing continuous confirmation of special relativistic effects. Neutron stars represent nature's most extreme time dilation laboratories outside black holes. These incredibly dense stellar remnants pack more mass than the Sun into spheres merely 12 miles across. Surface gravity reaches 100 billion times Earth's gravity, creating gravitational time dilation effects visible across cosmic distances. The Crab pulsar, located about 6,500 light-years away, exemplifies these effects. This neutron star rotates 30 times per second, sweeping lighthouse-like beams of radiation across space. Observations reveal that time near the pulsar's surface runs approximately 30% slower than in the weak gravitational field. Surrounding Earth, binary pulsar systems provide even more precise laboratories. The Hulse-Taylor binary, discovered in 1974, consists of 2 neutron stars orbiting each other every 7 hours and 45 minutes. As these massive objects spiral inward due to gravitational wave emission, their orbital velocities increase, creating varying time dilation effects throughout each orbit. At closest approach, the pulsars reach velocities of approximately 1,000 miles per second, roughly 0.5% light speed, combined with intense gravitational fields. This creates time dilation factors reaching several percent. Radio telescopes can measure these effects by tracking tiny changes in pulse arrival times as the pulsars orbit. Black holes represent the ultimate extreme. The supermassive black hole at our galaxy's center, Sagittarius A star, demonstrates gravitational time dilation on cosmic scales. Stars orbiting close to this 4 million solar mass monster experience significant time dilation during their closest approaches. The star S2 follows an elliptical orbit, bringing it within 750 astronomical units of Sagittarius A star, roughly 18 times the distance from the Sun to Pluto. During closest approach, gravitational time dilation causes time to run approximately 10% slower for the star. Compared to observers far from the black hole, even more extreme scenarios exist near stellar mass black holes. The black hole in the X-ray binary system, a 0620-00, demonstrates time dilation so severe that infalling matter experiences dramatic temporal effects. Material spiraling into the black hole appears to slow down and freeze at the event horizon when viewed by distant observers, though it continues falling normally from its own reference frame. These natural phenomena provide cosmic proof of Einstein's predictions while hinting at the extreme possibilities that might emerge from artificial time manipulation technologies. The dream of controlling time transcends science fiction when we examine the theoretical pathways emerging from Einstein's equations. While practical implementation remains beyond current technology, the mathematical foundations suggest several potential approaches to artificial time manipulation, each with its own requirements and implications. The Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994, represents perhaps the most famous theoretical time manipulation concept. This solution to Einstein's field equations describes a space-time geometry where space itself contracts in front of a spacecraft and expands behind it, creating a warp bubble that could theoretically enable faster-than-light travel. Within the Alcubierre bubble, space-time flows around the enclosed region while the interior remains flat. A spacecraft inside this bubble wouldn't actually move through space at all. Instead, space would move around it. This eliminates relativistic effects for passengers while enabling apparent velocities exceeding light speed. The time dilation experienced would depend on the relationship between the bubble's motion and outside observers. However, the Alcubierre drive requires exotic matter with negative energy density, a substance that may not exist in nature. The energy requirements are staggering, initially calculated to exceed the mass energy of the observable universe. Subsequent refinements have reduced these requirements, but still demand exotic physics beyond current understanding. Rotating massive cylinders offer another theoretical pathway, first described by mathematician Frank Tipler in 1974. An infinitely long rotating cylinder of dense matter creates space-time distortions that permit closed time-like curves, mathematical paths through space-time that loop back to earlier times. The Tipler cylinder must rotate at significant fractions of light speed and possess enormous density to generate the required space-time curvature. Near such an object, the rotation of space-time itself, an effect called frame dragging, becomes so extreme that light cones tip over, creating regions where moving backward in time becomes possible within the local light cone structure. Finite length, rotating cylinders, while more realistic than infinite ones, cannot generate closed time-like curves extending to arbitrary past times. However, they might still create significant time dilation effects, allowing controlled manipulation of temporal flow rates within specific regions. Cosmic strings represent another exotic possibility. These hypothetical one-dimensional defects, in spacetime if they exist, would possess enormous tension and create unique gravitational effects. Two parallel cosmic strings moving past each other at high velocity could theoretically create closed time-like curves in the spacetime between them. The geometry around moving cosmic strings allows for time travel scenarios where observers could follow specific trajectories to arrive at earlier times. However, cosmic strings remain purely theoretical, with no confirmed observations despite extensive searches by astronomers. Traversable wormholes offer perhaps the most intriguing theoretical pathway. Unlike the non-traversable Einstein-Rosen bridges that collapse too quickly for passage, traversable wormholes would require exotic matter to keep their throats open. Morris-Thorne wormholes, described in 1988, outline the specific requirements for stable passages through spacetime. Creating a time machine from a traversable wormhole requires differential aging of the two mouths. If one mouth travels at high velocity or sits in a strong gravitational field while the other remains stationary, the mouths age at different rates. Eventually, entering one mouth could allow emergence from the other at an earlier time. The exotic matter required for these scenarios must violate the averaged null energy condition, essentially requiring regions where energy density becomes negative. While quantum effects can create temporary negative energy fluctuations, sustaining them on macroscopic scales poses enormous challenges. Casimir effect demonstrates that negative energy densities can exist in nature. between closely spaced conducting plates. Quantum vacuum fluctuations create measurable attractive forces corresponding to negative energy density in the region between plates. However, scaling this effect to useful levels for space-time manipulation remains far beyond current capabilities. Recent theoretical work has explored whether advanced civilizations might manipulate dark energy, the mysterious force driving cosmic acceleration, to achieve controlled space-time distortions. Dark energy appears to have negative pressure properties that might, under specific conditions, enable exotic space-time geometries. These theoretical pathways share common requirements that push the boundaries of known physics: exotic matter, enormous energy densities, and precise control over space-time geometry. While mathematically consistent within Einstein's framework, their practical realization awaits revolutionary advances in fundamental physics and engineering capabilities that may take centuries or millennia to achieve. Modern experimental physics continues to validate Einstein's predictions with ever-increasing precision, while pushing the boundaries of what we can measure and potentially manipulate. From basement laboratories to orbiting spacecraft, researchers are exploring the limits of time dilation effects and investigating whether controlled space-time manipulation might eventually become reality. The most precise time measurements in human history come from optical atomic clocks, which can detect time differences smaller than 1 part in 10 to the 18th power. These incredible instruments use laser-cooled atoms trapped in optical lattices, measuring atomic transitions with extraordinary stability. When separated by mere inches in Earth's gravitational field, these clocks detect gravitational time dilation, effects predicted by general relativity. In 2010, researchers at the National Institute of Standards and Technology demonstrated gravitational time dilation over height differences of just 33 centimeters. Their aluminum-ion optical clock detected the predicted time difference of 4 parts in 10 to the 17th power, confirming Einstein's equations at a scale never before accessible. The International Space Station provides an ongoing natural laboratory for relativistic effects. Astronauts experience both special relativistic time dilation due to their orbital velocity of approximately 17,500 miles per hour and general relativistic time dilation due to Earth's weaker gravitational field at 400 kilometers altitude. The net effect means astronauts age slightly slower than people on Earth's surface, about 0.007 seconds less per 6-month mission. While tiny, this measurable difference demonstrates that time travel to the future occurs routinely, even if imperceptibly. The Gravity Probe B mission, launched in 2004, provided unprecedented tests of Einstein's predictions about frame dragging, the rotation of spacetime itself around spinning massive objects. Using gyroscopes precise to billionths of a degree, the spacecraft detected how Earth's rotation drags spacetime along, creating measurable effects on the orientation of spinning gyroscopes in orbit. Laser Interferometer Gravitational Wave Observatory, or LIGO, has revolutionized our understanding of spacetime dynamics by directly detecting gravitational waves, ripples in spacetime itself propagating at light speed. These detections confirm that spacetime possesses physical reality and can be disturbed, stretched, and compressed by violent cosmic events. The merger of 2 black holes, first detected by LIGO in 2015, created spacetime distortions that stretched and compressed the fabric of reality itself as they passed Earth. The interferometer arms changed length by thousandths, the width of a proton, as gravitational waves passed through, demonstrating the dynamic nature of spacetime geometry. European Space Agency's upcoming LISA mission will detect gravitational waves from space, providing even more sensitive measurements of spacetime distortions. This space-based interferometer will use 3 spacecraft separated by millions of kilometers to detect waves from supermassive black hole mergers and other exotic sources. Particle accelerators continue providing natural time dilation laboratories. The Large Hadron Collider accelerates protons to 99.9999% light speed, creating time dilation factors exceeding 7,000. Particles that would normally decay in microseconds survive for milliseconds in the laboratory frame, living thousands of times longer than their natural lifespans. Research into exotic matter properties has intensified with discoveries in condensed matter physics. Metamaterials with negative refractive indices create optical effects that seemed impossible just decades ago. While these materials don't possess the negative energy density required for space-time manipulation, they demonstrate that exotic properties can emerge from careful engineering of material structures. Quantum field theory research explores whether the Casimir effect might be enhanced or controlled to create macroscopic negative energy densities. Theoretical work suggests that dynamic Casimir effects, rapid acceleration of conducting surfaces, might generate detectable negative energy pulses, though scaling to useful levels remains extremely challenging. The search for dark energy analogues in laboratory settings has begun, with researchers investigating whether the mysterious force driving cosmic acceleration might be reproducible on smaller scales. Understanding dark energy's properties could potentially open pathways to controlled space-time manipulation. Breakthrough Starshot, an ambitious project to send tiny spacecraft to nearby stars, will create the fastest human-made objects ever built. Laser-propelled nanosails could reach 20% light speed, experiencing measurable time dilation during their journeys. These missions will provide the first direct tests of special relativistic effects at substantial fractions of light. Speed.clock synchronization experiments continue pushing precision boundaries. Networks of optical atomic clocks connected by fiber optic links enable measurements of gravitational time dilation across continental distances, potentially detecting tectonic motions and underground mass distributions through their gravitational time dilation signatures. As experimental capabilities advance, researchers edge closer to scenarios where controlled time manipulation might transition from theoretical possibility to engineering challenge, opening unprecedented possibilities for humanity's relationship with time itself. Transforming theoretical time manipulation concepts into practical technology presents engineering challenges that dwarf any previous human undertaking. The gap between mathematical possibility and physical implementation reveals the staggering scale of development required to achieve meaningful control over temporal flow. Energy requirements represent the most immediate obstacle. Even modest time dilation effects demand enormous power expenditures. Accelerating a single kilogram to 90% light speed, creating a time dilation factor of approximately 2.3, requires energy equivalent to 21 megatons of TNT, roughly 1,000 times the energy content of all fossil fuels burned globally in a single day. The Alcubierre drive's energy requirements initially exceeded the mass energy of the observable universe, approximately 10 to the 69th joules. Subsequent optimizations by researchers like Chris Vanden Broek reduced requirements to roughly the mass energy of Jupiter, still equivalent to about 10 to the 64th joules. For comparison, total human energy consumption throughout history amounts to roughly 10 to the 21st joules. Creating stable wormholes demands even more exotic requirements. The exotic matter needed to keep wormhole throats open must possess negative energy density, violating classical energy conditions. While quantum effects like the Casimir effect demonstrate negative energy densities exist, scaling them to macroscopic levels presents unprecedented challenges. Laboratory Casimir forces generate negative energy densities of approximately 10 to the -9 joules per cubic meter between plates separated by micrometers. Scaling this to wormhole dimensions would require maintaining coherent quantum effects across meters or kilometers, far beyond current understanding of quantum field behavior in curved spacetime. Materials science faces fundamental limitations when dealing with extreme spacetime curvatures. Near the event horizons of black holes or within proposed time dilation devices, tidal forces would tear apart any known material. The gradient in gravitational acceleration across human-sized objects approaches billions of g-forces per meter. In extreme scenarios, neutronium, the ultra-dense matter composing neutron star cores, might survive such conditions, but exists only under gravitational pressures exceeding 10 to the 34 pascals, pressures that cannot be maintained artificially. With any conceivable technology, creating artificial neutronium for time manipulation devices would require compressing matter to nuclear densities while somehow preventing gravitational collapse. Containment systems for time manipulation devices present unique challenges since the devices would necessarily distort the space-time containing them. Conventional magnetic or electrostatic confinement becomes meaningless when the geometry of space itself changes. The containment system would need to somehow isolate extreme space-time curvatures while remaining outside their influence, a seemingly paradoxical requirement. Control mechanisms face similar paradoxes. Operating a time manipulation device requires sending control signals to equipment, experiencing different temporal flow rates. Communication delays become variable and potentially infinite near event horizons. Remote operation becomes impossible when the device's interior experiences time differently than exterior control systems. Precision requirements exceed anything in human engineering experience. Creating stable wormholes or controlled spacetime distortions would require positioning exotic matter with precision measured in Planck lengths, approximately 10 to the minus 35 meters. This scale is smaller compared to atomic nuclei than nuclei are compared to solar systems. Manufacturing tolerances at such scales face fundamental quantum mechanical limitations. Heisenberg's uncertainty principle prevents simultaneous precise measurement of position and momentum, making it impossible to position particles with the precision required for stable exotic matter configurations. Safety considerations introduce additional complexity layers. Uncontrolled spacetime distortions could potentially create black holes, tear spacetime fabric, or generate causal paradoxes with unknown consequences. The margin for error approaches zero when manipulating the fundamental structure of reality itself. Computational modeling of time manipulation devices requires solving Einstein's field equations in highly dynamic, non-linear regimes. Current supercomputers struggle with simplified scenarios involving two merging black holes. Modeling controllable spacetime geometries would require computational capabilities, orders of magnitude beyond current systems. Economic implications suggest that meaningful time manipulation technology would require global-scale resource allocation, comparable to constructing thousands of Large Hadron Colliders simultaneously. The specialized infrastructure, trained personnel, and research facilities would demand international cooperation on unprecedented scales. Environmental impacts of high-energy space-time manipulation remain unknown, but potentially catastrophic. Experiments with exotic matter might create long-lived unstable vacuum states or trigger phase transitions in quantum fields, with unpredictable consequences for the stability of matter itself. Quality assurance testing presents unique challenges, when the test results might precede the tests themselves due to temporal effects. Traditional engineering validation procedures break down when cause and effect relationships become ambiguous or potentially reversed. These engineering obstacles suggest that practical time manipulation technology, if possible at all, lies centuries or millennia in the future, requiring revolutionary advances in fundamental physics, materials science, and energy production that dwarf current human capabilities. The ability to manipulate time would fundamentally transform human civilization in ways that challenge our basic concepts of existence, progress, and meaning. As we stand at the threshold of understanding temporal control, we must contemplate implications that extend far beyond technological achievement into the very nature of consciousness and reality. Scientific research would undergo revolutionary transformation with controllable time dilation. Experiments requiring millions of years could be compressed into human lifespans by accelerating laboratory time flow. Evolutionary biology could observe speciation directly. Cosmology could witness stellar evolution in real time. Climate science could fast forward through entire glacial cycles to understand long-term patterns. Conversely, slowing time would enable unprecedented precision in studying rapid phenomena. Nuclear reactions, chemical bond formation, and quantum decoherence could be examined in slow motion, revealing details currently hidden by their brevity. The collision between microscopic and macroscopic timescales would dissolve, opening new frontiers of scientific understanding. Medical applications could revolutionize healthcare by manipulating biological processes' temporal flow. Cancer treatments might benefit from accelerated immune system responses while slowing tumor growth through selective time dilation. Surgical procedures could be performed in slowed time, giving surgeons subjective hours for operations lasting minutes in outside time. Aging itself might become controllable through differential time flow rates. Spending time in accelerated reference frames could enable rapid healing and tissue regeneration. Alternatively, slowing biological time could extend lifespans indefinitely from external perspectives, while maintaining normal subjective experience. Space exploration would be revolutionized by time manipulation technology. Interstellar journeys could be completed in reasonable Earth time through extreme time dilation, even without faster-than-light travel. Alternatively, accelerated time zones could enable rapid terraforming of planets or construction of massive space habitats. Communication across cosmic distances would require new protocols accounting for variable time flow rates. Messages sent between different temporal reference frames would arrive at unpredictable intervals, requiring sophisticated synchronization systems to maintain coherent conversations across time-dilated regions. Economic systems would face fundamental restructuring when time itself becomes a manipulable resource. Time-rich and time-poor regions could emerge, creating new forms of inequality based on access to temporal acceleration or deceleration. Financial markets would struggle to price assets when investment time horizons become variable and controllable. Interest rates and economic growth models assume uniform time flow, when some investments could mature in accelerated timeframes, while others develop in slowed regions. Traditional economic theory would require complete reconceptualization. New forms of temporal arbitrage might emerge, trading time itself as a commodity. Educational systems could provide unlimited learning time through accelerated personal reference frames. Students could experience years of subjective study time within days of external time, mastering complex subjects that currently require decades. However, this would create challenges in social integration and shared cultural experiences. Entertainment and art would explore entirely new dimensions when temporal flow becomes controllable. Interactive experiences could stretch brief moments into hours of subjective time or compress lengthy narratives into minutes. The boundary between virtual and temporal reality would blur as experience design incorporates time manipulation. Legal systems would face unprecedented challenges addressing crimes involving time manipulation. How would courts handle cases where cause and effect relationships become ambiguous? Criminal justice concepts like statute of limitations would require redefinition when temporal sequences become malleable. Philosophical implications touch the deepest questions of human existence. If time becomes controllable, does free will retain meaning when decisions could theoretically be unmade through temporal manipulation? Personal identity would face new challenges when individual life experiences could unfold across vastly different temporal scales. Social relationships would strain under temporal flexibility. Families and communities depend on shared temporal experience for bonding and cultural continuity. When individuals could experience vastly different subjective time flows, maintaining social cohesion would require new approaches to collective experience. Religious and spiritual frameworks would grapple with fundamental questions about eternity, mortality, and transcendence when time itself becomes manipulable. Concepts of afterlife, reincarnation, and spiritual progression would require re-examination in light of controllable temporal flow. The ultimate question remains whether humanity would retain its essential character through such profound transformation. Time manipulation technology would represent humanity's final conquest over natural limitations, potentially elevating us to godlike capabilities over the fundamental structure of reality itself. Yet this power would come with proportional responsibility. Wielding control over time would require wisdom transcending anything in human history. The choices made with such technology would echo across temporal dimensions in ways we can barely imagine. As we continue pushing the boundaries of physics and engineering, we edge closer to possibilities that once existed only in imagination. Whether humanity will prove worthy of such cosmic power remains the ultimate test of our species' maturity and wisdom as we reach toward mastery over time itself. Einstein's revolutionary vision opened the door to temporal manipulation. Now, centuries later, we stand poised to step through that door into a future where time itself bends to human will, forever changing what it means to exist within the flowing river of temporal experience.